Hello. Well, last time we were working and we had picked up with Watt's law that power is equal to current times voltage, and then before we were done we saw Ohm's law that voltage is equal to current times the resistance, and we had finished up talking about resistors, resistivity, and that type of thing. Well, what I'd like to do is I'd like to use these two, Watt's law and Ohm's law, and put them together and come up with some other useful relations for power. If I substitute this V into here, I could say then that power is equal to current times IR. So we would get that power is equal to I squared R. And if I solve Ohm's law, so V is equal to IR, if I say then I is equal to V divided by R and substitute that into Watt's law, so I'm going to get power is equal to V over R times V, I get then that power is equal to V squared over R. So let me sum that up. We could say that power was equal to, again, the original current times voltage. It could be equal to I squared times R, or it could be equal to V squared divided by R. And these are really quite useful. One thing in terms of the I squared R, that's kind of power there. This is the one I like because it's fairly important. If you look at a source here, and we look at some sort of a load, and this could be you plugging a tool in, working in the backyard. The source would be the outlet, your house, the electric meter, however you want to think about that, and then the load is the tool. You're going to have some resistance between there. You have a line like that, and I'll lump the resistance from the return line into there like that. And this resistance is going to be dissipating power, probably in the form of heat. Hopefully it's not light. Hopefully it's not glowing red hot yet. Something like that. Now this could also be, we could have the state of Oregon supplying electricity to California or something like that. So this would just be on a larger scale. Well, if you want to try and reduce this, obviously this loss here, you're paying for this power and you're not getting to use it to do useful work or something like that. You're losing power and not getting it to sell it to California, whatever the scenario might be. How do you try and minimize this? Well, if we have some current going through here, I, people will say, well, if you reduce R, well, if you drop R, if you look at power is equal to voltage times current, or you look at power is equal to I squared times R, there we go, there's the one we want. If we reduce R, if you reduce R by a factor of 50%, you're going to reduce your power drop by a factor of 50%. That's good. But if you reduce I, if you cut I in half, you're going to reduce this loss of power here by a factor of 4. And that's where we get big advantage, is in that one. So we'll try and reduce the current. Now someone might say, hey, if you're reducing the current, then you're not going to be able to deliver as much power. Well, we can come back to this one, and if I drop the current down, what do? I run the voltage up. So that's certainly why you see when we transfer power over long distances, we will be doing it at very high voltages and hopefully lower currents. And this is, of course, one of the problems with Edison wanting to electrify with DC. And I'm not trying to pick on him, but with DC, it became fairly difficult to transfer power over long distances. You'd end up with a power plant every so often because with AC, we can have a very simple, rugged, inexpensive device, a transformer, where we can bump the voltage way up and have the current go down. With DC, it's not so easy to do that. So AC has some real advantages there, and we'll see that when we start talking about AC towards the end of this and most of next term. But if you're going to send power long distances, you're going to try and do it at as small a current and as large a voltage as possible. Now in your backyard, you're probably, if you're just going to be running a power saw on an extension cord, you're probably not going to be putting a transformer and running the voltage way up and then dropping it down so you can use it, in that case you'll probably just try and minimize the resistance. And remember from our previous work that the resistance is equal to the resistivity times the length divided by the cross-sectional area, right? So as the length increased, the resistance got greater, and as the cross-sectional area decreased, the resistance got greater. So if you're going to buy that extension cord, that extension cord, you want to try and make the length as small as possible. Just because a 100-foot cord is on sale, you may not want to buy the 100-foot cord. You want to make the cross-sectional area as large as possible. That's where we talk about wire gauges. I might talk about a 10 gauge or a 12 gauge or a 14 gauge or a 16 gauge or an 18 gauge. If we look at wire size, this is large to small. And I'm not talking about the size of the insulation, just the size of the wire itself. So if we look at the sizes of extension cords, this is a really good cord as a 10 gauge cord, whereas 18 is a pretty shabby cord. You wouldn't want to try and run that very far or have anything very large on it. And these numbers continue on up and they continue down. You could, usually you're not going to get extension cords out of this range, but as far as wire sizes, this continues this way and that way. And it's a little bit unintuitive in terms of the smaller the number, the larger the wire size. And when it gets down to 0, then it starts having 2 zeros or double aught, triple aught, and so forth. So by reducing the resistance, by keeping the length shorter and the area larger, we can reduce the resistance and have a power savings. But more effectively, if we reduce the current, we get a tremendous power savings. So sometimes people talk about I squared R losses, and that's what they're talking about there. So very useful using Watt's law and Ohm's law. Well, we've talked about one resistor, and we said that, let's see here, I think we had an example here where we had the current through this thing was 3 amps. Maybe we said that we had 10 ohms. I think we used Ohm's law. V is equal to I times R, which was 3 amps times 10 ohms, which got us 30 volts, right? So we had 30 volts. We could have, if we wanted to talk about power, we could say that power is equal to, we could use V times I. So we have 30 volts times 3 amps, which is what, 90 watts? Or we could use I squared R, so we wouldn't even necessarily needed to have calculated that. We could just say that that's I squared, so 3 amps squared times the resistance of 10. So that's going to be 90 watts. Or we could finish up with V squared over R. What are we going to have here? The voltage. Let's say that we didn't necessarily know this. We were given the voltage. So we have 30 squared divided by the resistance of 10. This is what, 900 divided by 10, or 90 watts. So lots of ways of doing that. But this one here, I squared R, is really useful when you start looking at trying to not have the losses when you transfer large amounts of power or power over long distances. Well, what I'd like to do then next is look at what happens if I have multiple resistors. Okay, so let's say that I arrange my resistors like this. So I will put them, so I could say that I have R1 and R2 and R3 and R4. Maybe I'll be real mathy and say Rn. Okay. One thing a person might wonder is, could we convert this to one single resistor? The answer is absolutely. we could say that this equivalent resistor is going to be equal to simply the sum of that R1 plus R2 plus R3 plus R4 plus Rn. So we would sum up those resistors like that. Now, let me go ahead and put some sort of a source in here. If I put some sort of a source here, that would drive a current. I could talk about this current I1 and I2 and I3 and I4, I5, and I6. We got quite a few of those. And what could we say about the relationship of I1 and I2 and I3 and I4 and I5 and I6? We could say that those are equal to each other. This is an important point. Okay? Remember that current is the flow of positive things, or if you want to think about the flow of electrons or the opposite of the flow of electrons, however you want to do it, but it's something that's flowing. And at no point do we have it's not like we've got a leak here and we've got a bucket here catching these electrons or whatever that's dripping off of there. That is not happening. So whatever flows through here has to flow through there, has to flow through there, has to flow through there, and so forth. So we can say then that the current through elements in series, because that's what this is, this current through elements in series is the same. Okay, going back to the notion that this is series, this is like trains on a track. You have a train car here, and it's hooked, one end of it's hooked to the next car, and so forth. So series is like trains on a track, if you're having a hard time thinking about this. And this statement, I was very careful with my wording here. The current through, current goes through something. The current through elements in series is the same. So if I have some way of knowing and figuring out what I1 is, do I know what I6 is? Absolutely, because the current through elements in series is the same. Okay, so if they put resistors in series, and we want to come up with an equivalent resistance, because let's say that again we put this source here. This is probably a lot easier to analyze than that. Well, if there's series, there must be parallel, right? So let's look at that. So looking at parallel, we're going to put the resistors like this, or we would say possibly we put them across each other. You can say that this is R1 and R2 and R3 and R4. And could we come up with a single equivalent resistor? We absolutely could. That's going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R, maybe we'll say N, maybe we should say instead of 4 we'll say N, so we can sound very mathy. We've got something like that. So it's the inverse of the sum of the inverses. Okay, and there's an interesting case that comes up if we have two of these. So let me put in a side here. So let's say I just have two resistors. That sometimes comes up, R1 and R2. We could say that the equivalent resistor here is equal to, well, from that equation up there, it's 1 over R1 plus 1 over R2. If you get common denominators and whatnot, you'll recognize, doing a little algebra here, that it's R1 times R2 divided by R1 plus R2. So something that comes up when you have two resistors, you sometimes will say product over sum. So maybe you're working a study group with someone and two resistors, boom, they always have the answer real fast. How'd they do that? That's product over sum. Multiply them together, then divide by the sum of them, product over sum. So it's an interesting case when you have two resistors. Okay. Well, let's say that I do the same thing here. Let's say I put some source here. And I want to talk about the voltage. I want to talk about this voltage here, V1. Maybe I want to talk about this voltage here, V2. Maybe I'll talk about this voltage here. Hard time putting that in, but there we go, V3. And this voltage here, V4. What can I say about the relationship of V1 and V2 and V3 and V4? I know they're equal to each other. Okay, and this becomes fairly obvious when you think about building this. If we go down to lab, we are not going to build the circuit this way. Probably the way we're going to do this thing, we'll have a source, we'll have a couple wires that come out here, and then we'll just put our resistors in here. And we will have one connection there and one connection there. You're not going to get a piece of wire and solder it in there and make a connection, another piece of wire and solder it in there. No, you're going to make one connection like this. Much faster, a lot more reliable. So you have something like this. So then it becomes absurd that these voltages would be anything but the same. So V1 is equal to V2 is equal to V3 is equal to V4. And if I were to put that into text, I could say that the voltage across elements in parallel is the same. Again, very important. And here, I've chosen my words carefully, the voltage across. We don't have current voltage through, we have voltage across. Voltage across elements in parallel is the same. And again, being able to reduce this is important, because if we were to put this source here, which is going to be easier to analyze, this or this, probably this. And again, this notion that V1 is equal to V2 becomes very important, because if I can somehow figure out what the voltage across this one is, well, it has to be the voltage across that one. Okay. Well, the question comes up, maybe I'll start a clean piece of paper here. What happens when I add resistance in parallel, or what happens when I add resistance in series? So let me look at that. So I'll take an example, put some resistors in here. And talk about the equivalent. So I have R1 and R2 and R3, and if I add this resistor, what does it do to it? That's a series arrangement. What happens if I have a parallel arrangement? And these are important conceptual things to wrap our mind around as we start to study this. Okay, so looking in here, I have equivalent resistance. Looking in here, I have equivalent resistance. What am I going to do here? I've got R1, and R2, and R3. And let's say I come along and I add this resistor here. When I add resistance, when I add this, it increases. So R equivalent goes up. When I add this resistor, R equivalent, you look at the math on it, R equivalent goes down. Okay. So when I add resistance in series, it increases the total resistance. That's pretty straightforward because you're just adding these up. When I add resistance in parallel, it decreases the total resistance, which if you look at the math being the inverse of the sum of the inverses, hopefully makes sense. Now from a practical sense, let's see how this works. Maybe we could give you a practical example. Let's talk about checking out of a store in a supermarket or something like that. So you've got your cart here all loaded up with all kinds of good stuff, and you're trying to get out of the store. And you have a register here, register there, and the registers that gives you resistance to getting out of the store, right? That impedes your flow of getting out of the store. So if it gets too hard to get out of the store, this line gets too backed up, there's too many people waiting, what does a good store do? Oftentimes a good store will add another register, they'll add another resistance, and that makes it easier to get out of the store, doesn't it? Conversely, some stores have a policy where they, you have to check out right here, and then they got a goon at the front door that wants to look at your receipt and whatnot. And what does adding that resistance? Maybe they got someone that follows you out to the parking lot and wants to look at it and inventory it as you put it in the trunk of your car. What does this all do to you getting out of the store or the parking lot? It increases that resistance, doesn't it? So if that example helps you to think about that, that's fine. If not, as the judge says, strike those remarks. So in short, when we have a series arrangement and we add resistance, we are increasing the total resistance. When we have a parallel arrangement and we add resistance, we are decreasing the total resistance. Well, let's look at some examples of this. Oftentimes students struggle with these types of problems, equivalent resistance and things like that. So let me come up with some problems here. Yeah. So let's say that we have, maybe we'll take this. Okay, what do I want there? Let's say that this is 1 ohm and 2 ohms. Let's say this is 6 ohms. This is another 6 ohms. 7 ohms. It's not going to work out. Yeah, maybe we'll get some funny numbers. That's fine. So let's say that we have 2 ohms here and 1 ohm there. Okay. So if I look in here and I want to try and find the equivalent resistance, so this is what I'm given, and let's say that I want to find the equivalent resistance. If I look here, it becomes very difficult to figure out what the relationship of these two resistors are. Are they parallel or series? Because we have this other branch here. So usually what I do is I go clear to the end and start working my way backwards. Okay. So if we go over here, it becomes very easy to see the relationship of those two. They're in series. So you're going to have 1 ohm plus 2 ohms gives me 3 ohms. Is that right? Okay. And so then at that point, I would redraw this thing. I'd spend the time to redraw it. I think that's a lot of people, when they run into problems here, they just don't spend the time to redraw this enough. We got something like this. There's 1 and 2. This is 7, 6, 6. What do we come up with here? 3. Okay. Now at this point, we look at the relationship of these. These are in parallel, right? So you could say, let's see, I have a 6 and a 3, so I have 1 over 6 plus 1 over 3, which would be the same as 6 times 3 over 6 plus 3, which is going to be 2, isn't it? 18 over 9 is 2. And then you could redraw this as So there's that 2 that we just found. There's this 6 that's still remaining. There's the 7. There's the 2. And there's the 1. Now some of you recognize that, hey, we've got all 3 of those that are in parallel, right? So you're going to have, with that, you would have 1 over 6 plus 1 over 6 plus 1 over 3, right? Which is what? I guess I could do it over here, because with this, I'm going to have product over sum. 2 times 6 divided by 2 plus 6 is 8. So I get 12 over 8. Is that 1.5? Is that what we get there with that? Let me double check. That should be. Yeah, 1.5. Okay. So probably doing it this way is a little easier if you don't have a calculator. If you got a calculator, then this is fine here. So whether you recognize all 3 of those were in parallel and you wanted to do it this way, or whether you wanted to divide it up and do it little by little, that's fine too. What you're going to come up with then is you're going to end up, I'm going to work my way across the page the wrong way here. So we still have this 1 ohm. We've got the 2 ohm. We've got the 7 ohms. And then we just found out that this was 1.5 ohms. I messed up when I wrote the problem. Should have picked numbers so I get a little better answer. But you've got this as it turns out to be 1.5, or you have the 3 of these that turns out to be 1.15. However you want to do that. This 2, of course, comes down to there. So we've got 1.5. I have 7, 2, and then 1 ohm. So we're going to end up with not a very nice answer. Well, what do we have here? That's series, isn't it? So you're going to have 7 plus 1.5, which gives you 8.5 ohms. So now I have 8.5 in parallel with 2, so let's redraw that. So this is 8.5, this is 2, and you have 1. So what's 1 over 1 over 8.5? Plus 1 over 2. .62 ohms. So that's what that turns out to be. And the equivalent resistance then would be equal to 1 plus 1.62, which is 2.62 ohms. So I should have picked a little better values. We wouldn't have had all those fractions, but when you get to working real-life problems, a lot of times you'll have decimals all over the place. Okay, let me double check that. We had 7 and 1.5, it's 8.5. .62. Usually use 3 significant figures, pretty standard for this type of business. 1.62. Yep, I think we're good with that. Okay. So the real key to this problem is figuring out where to start. If you start up here, it's very hard to figure out, is this resistor in parallel or series with this one? I don't know. So I go here, and then it becomes much more obvious. Those are in series, then it's in parallel with that. In fact, in parallel with that, then you can start to work back. So usually if someone's looking for the equivalent resistance here, you go to the extreme point and work back to that. And we'd come up with 2.62. So you could replace this whole mess with one resistor, that's 2.62. Let's try another example here, and I jotted this one down beforehand so I should have a little better numbers, hopefully. I think it comes out okay if I get it reproduced here, right? So let's try something like this. Now be careful if someone gives you a problem that has some of the values in ohms and some in k ohms. You want to make sure you have consistent units, dimensional homogeneity, all the same units. So convert all of your k ohms to ohms or all of your ohms to k ohms. So we'll say this is 50 ohms. So we got 50 ohms and 25 ohms and 15 ohms and 30 ohms. Then we've got 7 ohms and 16 ohms and 12 ohms and 4 ohms. Yeah. That should work out nicely. So again, if I'm looking to find the equivalent resistance, I could say that I can't start here. I got to start furthest away from it, which is probably going to be over there. What do I have there? Well, I have 4 ohms in series with 12 ohms, which is going to give me 16 ohms, isn't it? So now I have that 16 in parallel with that 16. Sometimes I'll shortcut that and write that as 16 in parallel with 16, which gives me what? Even split, so it's going to be 1 over 16 plus 1 over 16, which would be 16 times 16 over 16 plus 16. Turns out to be 8, however you do that, right? Anytime that it's the same value, it's just going to be half of that. So now I've got 8. Maybe that's worth redrawing that. Maybe I should have redrawn it more. Don't be tempted to take too big of steps as you're new to this. So we had 50 and 25 and 15 and 30. And what do we do? They came up with that as 16, and the 16 and 16 was 8, so I have this 7 ohms and this 8 ohms that I found right there. So what do we recognize here? What about the 7 and the 8? Those are in series. 7 ohms plus 8 ohms gives me 15 ohms, and that 15 is in parallel with that 30 now, isn't it? So I'll have then 15 in parallel with 30, which would be 15 times 30 over 45, which gives me, what, 10? Is that right? I think so. Let me double check that. Yep. So that's 10 ohms. So now I could redraw that, or a little more space here. What am I going to have? I'm going to have, still have this 25 here. So 15 ohms, 25 ohms, 50 ohms. I'm looking into those two terminals there, and I had, when I figured out that this was 15 and that was 30, when I put those in parallel, I came up with 10. So this is 10 ohms, isn't it? So now what's the relationship of these three? Well, I mean, if you imagined introducing some current at this point and the current came down here, it would have a choice. It could go this way or it could go this way, right? And if it chose to go this way, it would have to go through all of those. So we conclude that that 10, that 15, and 25 are what? They're in series, aren't they? So I have 10 plus 15 plus 25. And that's a good way of thinking about things. Imagine yourself as a current. You have some choices. You could go through the 50 or you go down here. So you sum this up. That gives me what? 50 ohms Very nice 50. That's much better, but there's 50. So now I could say that I have something like this. I've got this 50 up here that we started with. Oh, come on. That 50 up there, and then I combine those into a 50. So what's the relationship there? It's parallel. I have 50 in parallel with 50, which is going to give me 25 ohms. So I could say that R equivalent is 25 ohms. And again here, you recognize that these are in parallel, because if I say that I have some current and I happen down here, I have a choice. I can go this way through this 50 ohms, or I can go that way through that 50 ohms. Okay? So you've got some homework problems in terms of equivalent resistance and whatnot. Make sure that you're practicing on those. I'd like to look at, try, maybe not be successful, but try one more problem. So let's try something that looks like this. Let's say that we have something like this. And I won't necessarily put numbers in there. So looking in here, I'd like to find the equivalent resistance. And I've got a resistor here, a resistor there, a resistor there, a resistor there, and a resistor there. And this is actually a fairly tough problem, because if I look at these two, we might be tempted to say, well, they're in parallel, but no, this one exists in here. If I look at this one and that one, I might say, well, it's in series, but no, we've got those in there. This becomes fairly difficult, and what you're going to have to do when you solve this problem is you're going to have to use delta to Y conversions. Delta to Y. So you can convert a delta to a Y, or you can convert a Y back to a delta. So if I were to look at this, I could redraw this and say I have effectively something that looks like this, just changing this a little bit. I mean, pulling that apart. This is really how we build it in the lab anyway. So we have a delta here. So there's our delta, isn't it? And if I convert that to a Y, I'm going to end up with a Y, in this case, an upside down Y. Okay, and then I'm going to put that resistor and that resistor back in there. I'll circle those so you know where they came from. Now, with this, what do I have? Well, I know that these two are in series. Likewise, those are in series. Then that combination is in parallel and in series with that one. So I can actually solve this. So I don't want to belabor this delta to Y. A lot of times students they'll get a problem like this and they'll try and use delta to Y. Most of the problems we tackle will probably not be delta to Y, but it does come up. You might ask, well, how do I convert this delta to the Y, or if I have a Y back to the delta? Usually there's some equations. Your author has equations. Here we go. If you have a delta, then you can convert that delta to a Y, or if you have a Y, you can convert it to a delta. So you see equations like this in your textbook. I think what page I'm up to, this would be page 10. Okay. So don't think that it's always a delta or Y, but if you get something and it truly, like this, is not, this relationship's not in series, it's not in parallel, you might think about a delta to Y conversion. It's just a matter of going and getting the equations. I think you've got a homework problem like this. One of the things to be careful of is sometimes they will number these A, B, C, and this 1, 2, 3, so you have to be a little bit careful that however the figure is annotated, that matches the equations. But once you have the figure and the equations, you can go through it pretty quickly. The Wheatstone bridge here is something that comes up once in a while. If you're going into electrical engineering, you could play around a little bit with that. Oftentimes what you do with this is you put you might have an unknown resistance here, and then you put a variable resistor here, and with an amp meter, very fine, maybe a galvanometer that can measure very small currents, you can figure out what that resistance is. There's a lot of bridge circuits or Wheatstone bridge circuits, so I just had a little extra space, so I put that on there. But this is probably worth remembering. I think it's in your textbook. Well, I know it's in your textbook. I don't know whether they put the numbers in. Depends on what edition you have, whether they use numbers and letters or letters and numbers. If you go to a lot of online sources, they'll have something like that. But in this particular problem here, we would have had to have used that to go from the delta to the y. And you've got a homework problem like that, so you'll get some practice with that. Well, when we get together next time, we're going to talk about Kirchhoff's laws, which is really very important laws, foundational. Kirchhoff's current law and Kirchhoff's voltage law. So that should be fun, and we will do that next time. Thanks for watching. Take care till then.